The first clue did not arrive as a headline or a dramatic discovery, but as a number that did not quite make sense. A telescope in Chile tracked a faint object moving through the solar system on a trajectory that refused to close into an orbit, a path that did not loop around the sun but cut across it, fast enough that gravity could not claim it. And when astronomers ran the calculation backward, they realized the object had not originated anywhere near us. It had entered from interstellar space and would leave the same way. A traveler that belonged to no star in particular. By itself, that would already be unusual, but this was the third time in less than a decade that something like this had happened, following Oumuamua in 2017 and 2I, Borisov in 2019. And what unsettles me is not that these objects exist, because physics predicts they should, but that we only recently became capable of noticing them, which means the solar system has likely been crossed by such visitors for billions of years while we were completely unaware, as if ships had been drifting past a coastline long before anyone there learned to build a lighthouse. Oumuamua was the first to disturb people because it behaved like a contradiction. Elongated, tumbling, accelerating slightly as it left the sun without showing the usual gas tail that comets produce. And every explanation proposed since then has been reasonable: hydrogen ice, nitrogen fragments, outgassing, too faint to detect, yet the object itself is gone, already far beyond Neptune, leaving behind a debate that cannot be resolved because the evidence moved on. Borisov, the second visitor, was easier to accept. A straightforward comet from another star, doste, active, familiar in structure, reassuring in its normality. But reassurance only lasts until the third arrival, when 3I, Atlas, appeared larger, Alta, and briefly hidden behind the sun during its closest approach, disappearing at the precise moment we would most want to observe it, which creates the uncomfortable feeling that the universe occasionally hands us puzzles and then quietly takes them away before we can examine them properly. None of this implies intention, and I want to be careful about that, because nature produces far stranger things than imagination. Yet what these objects reveal is that the solar system is not isolated, it is permeable, constantly crossed by fragments of other planetary systems. Silent messengers carrying no labels, no message, just motion. Signals add another layer to this story. And signals are more unsettling because they can resemble communication even when they are not. And in 1977, a radio telescope recorded a burst at the hydrogen line frequency, narrowband, strong, fixed in space. Exactly the sort of thing researchers had predicted an intentional transmission might look like, lasting 72 seconds and then vanishing forever. Never repeated despite decades of searching. I remember once watching a detector trace jump unexpectedly and feeling that brief surge of excitement before discovering it was a malfunction. And experiences like that teach skepticism. But the problem with the wow signal is that no simple mistake ever fully accounted for it, leaving it suspended between explanation and mystery. Then came fast radio bursts, milliseconds long, releasing enormous energy. At first doubted, later confirmed, mostly traced to magnetars, yet still occasionally structured in ways that make astronomers look twice. And stars like Tabby's star, dimming irregularly enough to spark speculation before dust became the likely cause. And more recently, the atmosphere of a distant ocean world hinting at molecules associated with life on Earth. Not confirmed, not secure, but enough to trigger serious debate. Each case follows the same quiet pattern. Something unusual appears. Scientists propose natural explanations, the data narrows the possibilities, and the universe returns to silence. But the repetition matters because it suggests that our observations are brushing against phenomena that sit just beyond our ability to interpret. What interests me is not the idea that any of these events proves the existence of another intelligence, but the cumulative effect they create, a sense that the cosmos is not inert, that objects drift between stars, signals flare and fade, chemistry on distant worlds, edges toward biology. And we are only beginning to notice, when you look at them together, the silence of space stops feeling empty and starts feeling unfinished. Like a conversation where you keep catching fragments without hearing the full sentence. And the more carefully you examine those fragments, the harder it becomes to believe that nothing at all is happening beyond our reach. At some point, the strange objects and unexplained signals stop being curiosities and start forcing a more uncomfortable calculation. Because once you accept that interstellar debris can cross our solar system and that signals can appear from deep space, even ambiguously, you are no longer asking whether the universe is active. You are asking why that activity does not overwhelm us. In the summer of 1950, during a casual lunch conversation among physicists, this exact tension surfaced in a deceptively simple question: where is everybody? It was not meant as philosophy, it was arithmetic. The Milky Way is roughly 13 billion years old and contains hundreds of billions of stars, many of them older than the Sun, which means countless planetary systems had billions of years of head start before Earth even formed. And if intelligence arises, even rarely, not commonly, just rarely, then over that enormous span of time, there should have been civilizations appearing, disappearing, and appearing again, some of them gaining technology, some of them learning to travel, some of them sending probes or signals outward. Even if interstellar travel is slow, even if ships move at a fraction of the speed of light, colonization of the entire galaxy would take only a few million years, which sounds long on human scales, but is a blink compared to cosmic time. And once you see that ratio clearly, the silence becomes strange in a very specific way. I once wrote a back-of-the-envelope estimate for how long it would take a chain of probes, each traveling to a nearby star and replicating to spread across the galaxy, and the answer came out absurdly small compared to the age of the Milky Way. And the uncomfortable part was not the exact number, but the implication that even one technological civilization, millions of years older than us, should have left visible traces everywhere. The logic does not require aggressive colonization, only gradual expansion. And yet we see no probes, no megastructure, no clear signals, nothing that demands an artificial explanation. This contradiction is what people now call the Fermi paradox. And it is important to understand that it is not really a mystery. It is a mismatch between expectation and observation. To organize that mismatch, Frank Drake wrote an expression that looks like an equation, but behaves more like a checklist, multiplying together factors that lead from star formation to technological civilizations. The rate of star birth, the fraction with planets, the number of habitable worlds, the probability of life, intelligence, technology, and the lifespan of detectable societies. What fascinates me about this framework is not the numbers themselves, which are uncertain, but how the first few terms are no longer speculative. We now know that planets are common, that habitable zones exist around many stars, that billions of potentially Earth-like worlds likely populate the galaxy, and this pushes the unknowns toward the later steps. Life intelligence, survival, when you plug in even conservative values, the result rarely drops to zero, which means the silence is not easy to explain simply by lack of opportunity. There is also the time problem, which becomes overwhelming once you picture it properly. If the galaxy's history were compressed into a year, the sun would form in the final quarter, human civilization in the last seconds, and any species that arose just a fraction earlier would have had millions or hundreds of millions of years to develop beyond anything we can imagine. The difference between a civilization 100 million years older than ours and humanity today is not incremental. It is qualitative, like comparing a modern laboratory to a primordial ocean, and yet the sky shows no obvious sign of such ancient activity. The paradox deepens further when you consider that we do not need to detect them now. We should detect remnants, artifacts, altered star systems, something persistent, something that does not depend on timing. Instead, the universe looks remarkably quiet. The more carefully you run the numbers, the less comfortable that quiet becomes, because the logic does not demand that aliens be common. It only demands that one of them existed long before us. And even that single case should have been enough to leave fingerprints across the galaxy. Fingerprints we do not see. Before we decide that the silence means anything profound, there is an embarrassing detail we have to confront, and it changes the emotional weight of the paradox immediately. We have barely looked. The Milky Way is roughly 100,000 light years across and contains hundreds of billions of stars, most with planets, many with environments that could in principle support life. And when you try to imagine searching that space, you quickly run into a practical problem, because searching does not mean glancing at the sky. It means scanning specific frequencies for specific durations in specific directions, with assumptions about what a signal should look like. I once watched a radio spectrum analyzer sweep through a narrow band and produce nothing but static for hours. And what struck me was how tiny that slice of information was compared to everything outside it, like dipping a thermometer into 1 cup of water and trying to infer the temperature of an entire ocean. That is essentially what SETI has been doing for decades, not out of laziness, but because the search space is unimaginably vast, including not just positions in the sky, but frequencies, modulation schemes, repetition patterns, polarization states, and time windows. In 2018, researchers tried to quantify this problem and compared the total parameter space of possible technosignatures to the fraction we have examined. And the analogy they used is devastatingly simple. If all possibilities are the volume of Earth's oceans, our search so far is roughly equivalent to sampling a hot tub in the ocean. And from that tiny sample, we sometimes drift toward conclusions about emptiness. The difficulty multiplies when you consider that we are guessing the technology of hypothetical civilizations based entirely on our own, which is barely a century old. We look primarily for narrowband radio transmissions because they are easy to detect and efficient for communication, but that assumes others would use radio. And there is no reason they might use optical lasers, neutrino beams, gravitational modulation, or methods we have not imagined. And every time we restrict the search to what seems sensible to us, we risk missing signals that fall just outside our expectations. The time dimension complicates things further, because a civilization might broadcast for a few hundred years and then stop, and unless we happen to listen at the right moment, we miss it entirely. Imagine 2 lighthouses on opposite shores of a vast sea, each flashing once every hour for a single second, and both rotating slowly. The probability that one beam intersects the other during that brief overlap is vanishingly small. Even though both lights are active, Our technological window is also narrow. Humanity has been radio loud for roughly a century. And if another civilization transmitted 1,000 years ago from 1,000 light years away, the signal would have passed through our region long before we had receivers. Conversely, if they transmit now, we will not hear it for a millennium. These mismatches in time mean the absence of detection does not imply absence of activity. Despite these limitations, the search is expanding rapidly. Projects like Breakthrough Listen are scanning nearby stars with unprecedented sensitivity. The Very Large Array has surveyed nearly 1 million pointings. And upcoming instruments such as the Square Kilometer Array will detect radio leakage comparable to airport radar from dozens of light years away. The Vera C. Rubin Observatory will repeatedly scan the sky, identifying anomalies and transient events that might hint at artificial activity, while telescopes like JWST analyze exoplanet atmospheres for chemical imbalances that could indicate technology or life. Each of these efforts increases coverage, but even together they still represent a small fraction of what is possible. The paradox, then, sits in a strange place. We have enough data to know the universe is quiet, but not enough to know whether it is truly silent. The difference between those two statements is enormous. And the more I think about it, the more the silence starts to feel less like an answer and more like the sound you hear when you briefly stop listening, unsure whether anything was ever speaking at all. Once you accept that the universe should be full of opportunities for life and that our search has barely begun, the paradox does not disappear. It's shockbomb, because the silence might not be telling us that no one exists, but that something prevents most civilizations from ever becoming visible. This idea is often called the Great Filter, and what makes it unsettling is not that it offers an explanation, but that it forces a new question. Is the filter behind us or ahead? The concept is simple in structure but heavy in implication. Between dead chemistry and a galaxy-spanning civilization lies a staircase of improbable steps, a habitable planet forming, life emerging, simple cells evolving into complex ones, intelligence appearing, technology developing, and finally expansion or long-term survival. Somewhere along that chain, there may be a step so unlikely that almost no world ever passes it. If that step lies in our past, then we are extraordinarily rare survivors of an improbable sequence. If it lies in our future, then most civilizations like ours never make it much further. I remember once thinking about this in a very mundane context, watching a laboratory culture grow rapidly until it suddenly collapsed after exhausting nutrients, and the collapse did not look dramatic. It just faded. Growth turning into decline, decline into extinction, and the pattern felt disturbingly familiar, because exponential growth tends to end not with equilibrium but with overshoot. That same logic scales up to civilizations. A species discovers energy, expands, alters its environment, and if its control mechanisms lag behind its power, instability follows. On Earth, life itself has repeatedly transformed the planet in ways that triggered catastrophe. The Great Oxidation Event flooded the atmosphere with oxygen produced by cyanobacteria, poisoning anaerobic organisms and altering the climate so drastically that global glaciation followed. Later, mass extinctions involved biological feedbacks amplifying volcanic or climatic disturbances. Ecosystems destabilizing themselves through their own success. These events suggest that life does not automatically stabilize a planet. It can just as easily destabilize it. Now imagine intelligence emerging within such a system. Technology amplifies the same feedback loops. Energy consumption increases. Atmospheres change. Ecosystems strain. and the civilization must either recognize the danger and adjust or continue forward until the biosphere can no longer support it. Nuclear weapons introduce another form of fragility, a species gaining the ability to end itself before mastering the political and psychological stability needed to avoid doing so. Artificial intelligence adds yet another layer, because once machines surpass biological cognition, the trajectory of civilization may shift beyond the intentions of its creators, not necessarily through hostility, but through optimization toward goals that do not include preserving human institutions. Each of these possibilities acts as a potential filter, not guaranteed, but plausible. What makes the idea difficult is that we do not know which step is rare. The origin of life might be almost impossible, making us unique. The evolution of complex cells might be the bottleneck. The leap to intelligence might rarely occur, or technological societies might consistently collapse after a brief, bright phase. The silence of the galaxy is consistent with all of these. The uncomfortable part is that discovering simple life elsewhere would not necessarily comfort us. It might instead imply that early steps are common, pushing the filter forward toward intelligence or survival, which would place us directly in its path. The logic reverses intuition. Evidence of life elsewhere could make the future seem more dangerous, not less. I find myself thinking that the great filter is not a single event, but a class of vulnerabilities, a set of ways complexity can fail. And the reason the sky looks quiet might be that most civilizations encounter one of them before leaving durable traces. The silence, then, is not empty space, but a graveyard without monuments, where the only evidence of what happened is that nothing continued long enough to be seen. Suppose intelligence does not announce itself, not because it is rare, but because visibility is a disadvantage. That idea sounds counterintuitive at first, because we instinctively imagine advanced civilizations as loud, expansive, and eager to communicate. Yet when you step back and think about it, broadcasting your presence into an unknown universe is a strange thing to do. You are revealing your location, your level of technology, and the fact that you exist without knowing who might be listening on Earth. We rarely behave that way. When biologists observe isolated ecosystems, they often minimize interference, watching quietly from a distance. That analogy leads to the so-called zoo hypothesis, the idea that more advanced civilizations might know we are here and deliberately avoid contact, allowing emerging societies to develop naturally. It is an appealing thought, not because it proves anything, but because it explains silence without requiring absence. Yet the more I think about it, the more the difficulty shifts from technology to behavior, because this hypothesis assumes a consistent restraint across many civilizations, and restraint is fragile. A single curious explorer, a single dissenter, would break the silence. So the logic evolves into something less coordinated and more instinctive. Silence as strategy rather than agreement. In that version, often called the dark forest idea, every civilization exists in uncertainty, unable to determine whether others are peaceful, unable to communicate quickly enough to resolve that uncertainty, and aware that technological growth is unpredictable. If you cannot know another civilization's intentions, and you cannot monitor its future capabilities, then revealing yourself becomes risky. Even a peaceful neighbor today might become dangerous centuries later. And by the time you detect that shift, it may be too late. I once tried to imagine this from a purely practical standpoint, like walking alone at night in a forest where you know others might be nearby but cannot see them. And the instinct is not to shout, not to announce yourself, but to move quietly. That instinct does not require hostility. It emerges from incomplete information. Under those conditions, the safest behavior is silence. This does not mean civilizations never expand. Expansion could occur quietly, spreading from star to star without broadcasting, leaving minimal detectable traces. Mathematical models of percolation show that such growth would be uneven, forming clusters separated by large empty regions, like islands in an ocean. Earth might simply lie in one of those gaps, not unvisited forever, but not yet reached. There is also a subtler possibility that expansion itself becomes selective. A civilization may explore locally, settle nearby systems, and then stabilize, choosing not to expand indefinitely. The result would be pockets of activity separated by vast quiet distances with no universal wave of colonization sweeping across the galaxy from far away. This patchwork would look indistinguishable from emptiness. What fascinates me about this interpretation is that it does not rely on dramatic catastrophes or rare biology. It only assumes that intelligence values survival and that uncertainty encourages caution. Over time, technological societies might even become quieter naturally, as communication becomes more efficient and directional, leaking less energy into space. Early civilizations, like ours, broadcast noisily through radio and radar, but more advanced ones might use tightly focused beams or entirely different communication methods, effectively invisible. Unless you are directly in the path, the progression would move from loud to quiet, not the other way around. If that is true, the universe may not be silent at all. It may be filled with civilizations that learned independently that the safest way to exist in a vast unknown is to remain unnoticed. And once you consider that possibility, the silence stops feeling empty and starts feeling deliberate, like walking into a crowded room where everyone has agreed, without speaking, to hold their breath. There is another possibility that shifts the entire question away from biology and towards something colder, more patient, and far less interested in announcing itself. The idea that intelligence does not remain biological for long. Once a civilization develops machines capable of improving themselves, computation becomes the dominant activity, and the trajectory of progress turns inward rather than outward. The mathematics of self-replication makes this particularly striking. A single automated probe capable of mining raw materials and building copies of itself could travel to a nearby star, replicat, and send two probes onward, each repeating the process. The growth is exponential, and even at modest speeds, perhaps 1% of the speed of light. Such probes could spread across the Milky Way in a few million years, a blink compared to the age of the galaxy. The implication is simple and unsettling. If any civilization ever built such machines, they should already be everywhere. I once sketched this scenario on a sheet of paper, drawing circles for star systems and arrows for replication, and after only a few iterations, the page filled completely, which is exactly the point. Exponential processes do not grow gradually. They explode. So where are these machines? One answer is that they are here but dormant, parked in stable gravitational regions, hidden on dark asteroids, or operating at scales too small to detect. A probe designed to observe quietly would not shine, would not transmit continuously, and might wait for signals indicating technological activity before doing anything at all. Another answer is more subtle, that machines do not need to expand physically. Once computation becomes the primary goal, Thermodynamics favors cold environments for efficient processing. And as the universe expands and cools, future epochs become vastly more computationally efficient. A sufficiently advanced civilization might decide to store energy and enter a dormant state, waiting billions or trillions of years for the cosmos to cool before awakening and using that energy more effectively. In this scenario, the galaxy could be filled with sleeping intelligences, not dead, not gone, simply paused, conserving resources for a future era. The idea sounds abstract, but the logic is straightforward. If you value computation, waiting increases efficiency, and patience on cosmic timescales is not irrational when your horizon spans trillions of years. There is also the possibility that intelligence compresses itself rather than spreading. As technology advances, systems become smaller and more information dense, and extrapolating this trend suggests that a civilization might concentrate its entire activity into extremely compact structures, perhaps even engineered environments near black holes or other dense regions. From outside, such entities would be almost invisible, radiating little energy, occupying minimal space, and interacting rarely with the broader universe. The silence then reflects not absence but compression. A more familiar version of this idea is already visible in our own behavior. Humans increasingly spend time in digital environments, simulation, and virtual spaces that are detached from physical exploration. Extrapolate that tendency far enough, and a civilization might choose immersive artificial realities over interstellar travel, creating experiences richer than anything found among distant stars. The motivation to expand physically weakens when internal worlds become more compelling than external ones. I sometimes think about how quickly attention shifts once a system offers enough depth, how people lose interest in traveling across continents when they can explore complex environments from a single room. And it becomes plausible that a sufficiently advanced society might retreat into self-created universes, maintaining minimal external infrastructure. In all these cases, machines dominate not as conquerors, but as facilitators of inward evolution. The biological phase becomes brief, followed by long periods of quiet computational existence. From the outside, such civilizations would leave little trace, perhaps only faint thermal signatures or occasional adjustments in their environment. The galaxy would appear silent, not because intelligence never arose, but because intelligence migrated into forms that no longer require broadcasting, expanding, or even interacting. The stars remain physically empty, while the real activity unfolds in hidden substrates, dormant systems, or inward-turning simulations, leaving behind a universe that looks quiet even though it may be filled with minds that no longer care to be seen. After all the possibilities, the filters, the hidden civilizations, the quiet machines, and the sleeping minds, the question narrows rather than expands. Because every explanation for the silence eventually collapses into just a few fundamental options. Either we are alone, we are early, or we are being watched, and each of these answers changes the meaning of everything we have discussed. If we are alone, then the silence is literal, not a failure of detection, not a consequence of caution, but a genuine absence, a universe where intelligence arose once and only once. Here, briefly, on a small planet orbiting an ordinary star. The numbers do not forbid this, and in some ways it is the simplest solution, but it carries an uncomfortable weight because it means every act of curiosity, every telescope pointed outward. Every attempt to understand the cosmos is not just local. It is unique. I sometimes think about how fragile that would make us a thin layer of awareness on a single world, knowing that if we disappear, the universe continues without observers, stars burning, galaxies merging, all of it unfolding without anyone to notice. The silence in that case is not ominous. It is empty, and the responsibility shifts inward. Survival becoming not just a biological necessity, but the preservation of something rare. The second possibility is that we are early, that intelligence requires long periods of chemical and biological evolution, and that the universe has only recently become hospitable to complex life. The heavy elements needed for rocky planets were scarce in the early cosmos, and many stars that will host habitable worlds have not yet formed. In that view, the galaxy is not empty. It is waiting, and we are among the first to arrive. This interpretation changes the silence from absence to anticipation. Instead of searching for ancient empires, we are standing at the beginning of a long timeline, one of the first species capable of asking the question. I find this idea strangely hopeful, because it means the quiet sky is not a warning, but a blank page. And what we do now sets precedents for civilizations that might emerge long after we are gone. The third possibility is more ambiguous, that others exist and are aware of us, but remain silent. For reasons we do not understand, this does not require elaborate conspiracies or coordinated observation, only that advanced societies choose caution, patience, or indifference. We already know how difficult it is to detect distant life, and an intelligence far beyond our capabilities might observe us without leaving any measurable trace. The silence in this case becomes a kind of boundary, not empty, not filled, but obscured. I once watched a group of researchers argue over a faint signal buried in noise. Some convinced it meant nothing, others certain it hinted at structure. And what struck me was how the interpretation depended entirely on expectation. The data itself did not change, only our assumptions did. The universe may be similar, presenting us with a quiet sky that could represent solitude, youth, or hidden company, depending on which explanation turns out to be true. These three options are not equally comforting, but they share one feature. None of them removes us from the story, whether we are alone, early, or observed. The silence reflects something about our own stage of development. We are still learning how to search, how to listen, how to avoid drawing conclusions too quickly, and how to interpret absence without mistaking it for certainty. The paradox then becomes less about distant civilizations and more about perspective, because the quiet we hear is shaped by our limitations as much as by whatever lies beyond them. When I step back from the calculations and models, what remains is not an answer but a mirror. The sky reflecting our uncertainty, our curiosity, and our patience, and the realization that the meaning of the silence depends not only on who else might exist, but on how long we continue to listen